Join me in welcoming Xavier.
Hi, everyone. My name is Xavier. I work for Data61. I've only been on the team for about 3 months, and it's sort of my first functional programming production journey. So I'm all very new to Haskell, I'm using Elm at the moment, and this morning I've heard about Elixir and Clojure, so it's like very daunting. But in my spare time, I do a bit of experiment hobby with generating graphics. I kind of dabbled into music a little bit and then got out of it, and now I'm back into graphics. So I thought, why not apply a language that I'm using at work also in terms of generative art? And that kind of turned into a different talk that was given as a 5-minute talk in What Do You Know in Melbourne, which then I thought it would be nice to kind of broaden it to be a 30-minute proper talk. And then Linda Jen came around, so I thought, yeah, why not? I'll put it in, and I got in. So here I am, and see how we go. This is my little pen plotter. You will see that plotter in action hopefully halfway and at the end of the talk. It's just a thing I got, you can buy from the Emo Math Scientist for about 400 USD, refurbished, and supposedly lifetime warranty, so yeah. This is my first plot that I've done with the pen plotter after all the calibration. There's a lot of weird things about it. Like, you wouldn't expect the printer to work when the ground isn't even. Then you realize if the ground isn't even, there's no way the pen can plot. So there's a lot of things that I have to kind of tweak around to make sure it works. But once you get the thing going and you know what you're using in terms of the thickness of the pen and the color of the pen, you can run different iterations. You get different, very nice results. And I strongly recommend you to check out Twitter hashtags. There's like 4 or 5 of them, but the bigger ones are Plotter Twitter, which is focused on the pen plotter itself, and also just in general Generative. So there's a lot of artists and people's sort of prior work that I look up to, and then sort of their work is kind of inspired some of the examples and the algorithms I'm going to introduce you today. So this is going to be mostly in Elm because that's the language of choice that I've decided to use. And Elm, as you may know, can do lots of things, including generating SVGs, because SVG is part of the web spec. And then at some point, I have to kind of talk to JavaScript a little bit because I'm talking over the network. And there's a couple of things you can do in Elm over the network, but also a couple of things you can't really do because it's kind of in a messy world. So I defer back to JavaScript, and eventually that goes to the pen plotter. So this talk kind of focuses on mainly just the first Elm to SVG part, and then there's a little section side note on the JavaScript to the pen plotter part, and the source code, everything is going to be fully on GitHub online. If you can search for it right now, it's already online, just so you know where the focus is going to be. So, and the other aim is I really want to demystify creative coding for functional programmers, because sometimes people have this idea of, oh, you're a logic person, the logical brain, the creative brain, the whole, that's really a myth. Eventually, that whole left and right side brain thing was kind of disproven in a way that, people who's doing programming or people who's doing sort of logical work can actually be very creative as well, as you've seen in the keynote this morning. Eugene, it was awesome, so love that talk. And I want to kind of give you some tools you can take away if you haven't done any creative coding before. If you have, I want to give you some more tools you can take away, either in Elm or SVG or the pen plotter, so hopefully there's a bit of things for everybody. So the 3 things I'm going to show you today, we're going to start with a random grid. It's going to be super simple, but that shows you the structure of the program and how I've developed this thing in Elm. And then there's 2 more sort of algorithmic techniques that I'm going to introduce, which is Chevalier random numbers by inconvergence and L systems from Lindenmayer back in '68. So hopefully that will give you a bit of a splash in flavors as well. OK, so let's jump straight into it. We have a line. This is just a line. It's not very exciting. It's a line. You can draw these lines in a grid. And if my laser pointer works, you can kind of see that, yeah, you can kind of draw them in like 4 by 4. You get a bit of a stripy hash pattern. And this is something that people have done quite a bit in the creative coding community as introduction. Just all you have to do is just to rotate the line a little bit. Suddenly, you get this really interesting pattern. And then you just increase the repetition of, maybe by 16 by 16. You can draw as big as you like, as much as your computer will compute. And you get this really, really nice pattern that seems random. And it is random. But you get a nice repetition out of just basically lines and rotations, right? So it's a nice sort of easy to understand concept, and we're going to build this in code, OK? So now, because this is going to be done in code, and I apologize that this code is going to be a little bit code heavy, then I realized this morning has been just code heavy anyway, and so hopefully it won't be too bad for you. All right, so we're going to start by making a grid. This is a recipe I took from the Elm documentation. You can just generate a permutations of 2 things out of I guess, two lists of numbers. So in this case, I wanted to generate a grid where I can say I want to go from 0, 0 to 15, 15, and I want to have 0 to 15, 0 to 15, and I want to get all the permutations of those two together. Then I get that function, which then just takes an x and a y, which is going to be two dimensions of the array, if you will, and then generates all the combinations. So I just kind of use that straight off the bat. And drawing a line is pretty easy. You just generate an SVG in Elm. Elm has abstractions for HTML and SVG, both in the properties and the children's. For the nodes, it's kind of one-to-one. So if you're familiar with SVG, you would know that you can draw a line just by specifying the 2 points of the line, right? So that's that function. OK, so generating random rotations. Pure functions, random numbers, how does this work? It's a bit weird. Elm gives you this awesome tool called the plunger. And we're just going to take the plunger and do this, right? So it's going to be OK. We can do it together. Right. So the program structure we're about to plumb looks like this. If you have done Elm before, this will be somewhat familiar to you because you can see there's the model and the message. Init, update, and view. They're all kind of built-in standard Elm architecture, sort of like conventional model. If you haven't used Elm before, I'll just quickly tell you about it. The model is where you sort of store your page state. It's not really a mutable state. The state gets passed around. So in a sense, it's immutable, but it's created every time as you update. The message tells sort of the Elm program what kind of thing am I updating this time, so you can sort of define your own message per the page. Init gets called once by the Elm program. So in this case, I'm just calling update just because I can. Update takes the message and the model, and then depending on the combinations of whatever you want, you can decide pattern match on that and just do something about it. In this case, I'm generating some random values, and then once it's done generating, I'm going to draw them. And then the view just kind of tells how to render, so how to convert the model object into HTML. In this case, SVG. But anyway, so let's get started in this. We're going to define our own generator and model. So in this case, I've decided that I want to be flexible about how I can define the size of the grid. So I'm using int and integers to say the width and height of the grid, shall we say. And I'm going to add a little bit of a list float. That's just kind of my list of random numbers that's going to be generated in the model. So I then match the message to that. I have a generate message, just generate me stuff. And then once it's done, I pull it into the model. So the init function just calls generate, and I'm just going to specify a starting grid of 16 and 16. And then the next bit is kind of like the interesting part of how you do random generation in Elm. It has a built-in random module. It's quite powerful. It has all the basic things you would expect, like generating a float between two values. So here I'm just going to say, yeah, negative and positive 0.5. Why not? Let's do it. And I'm just going to quickly wrap that thing in the thing that gives me a list of random numbers back, because I do this a lot. So I got tired of writing random.list something value, so I just put it into a function. So it's easy. And then this is where it gets a little bit weird to kind of put into the update function. So how do you tell Elm how I can get some random numbers out of it? Well, luckily in Elm, it has this construct called the command. The command is kind of Elm's way of saying, I'm going to do something on the side. That's not quite pure, but I can wrap it up in a pure way. That doesn't quite disrupt the program logic. Everything will still type check, but I can affect something into your program again in the next update, right? So in this case, I can use the random.generate function that produces a command, which wraps a message, and the message just tells me, oh yeah, I can generate some stuff, and I'm going to put it into the model again. So I've got my random list of m times n, that being my size of my grid. So that will give me the exact number of elements in the grid. And then I'm just going to plug it straight into the draw message, which would then trigger the draw message down here. So the update would just get called twice, basically. And then it just that's where I pattern match sort of everything to create my model, with my initial state and the generated stuff, which the viewer will go, OK, you got a model. I can draw it now, right? So it's kind of like I want to generate something once. It's a very simple pattern to start with. Then lastly, we're going to draw our grid of lines with random rotations. I like to think of things in maps, so just list.map, because it's the most straightforward way to say, I want to iterate through something. And in a pure functional way, it's really weird to say, how can I iterate through something and I have this other thing that I have no plugin? It all gets a little bit kind of out of hand. So you want to separate your random list of models from the initial state that you're going to draw, such as lines. And you also want to separate the other ones that may have some side effects, like you want to move the line a little bit, or you may want to apply some random values. So once you can identify these separate things that you want to put together in your view or composition, whatever it is, you can then easily just say, well, here's my arguments, bam, 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 list.map. So it's not necessarily the most efficient way of doing things, but definitely an easy way to kind of think about it, at least to reason about your program. So here's the elements built-in function to generate a group. A group can contain one or more visual elements. In this case, I'm just putting a line per group. And the thing about group is that it lets you apply a transform property, which in the browser just kind of moves it around. So I can move the line a little bit this way and this way and this way. So even though I'm drawing the same line at -0.5 to +0.5 in both x and y, I can move it in the x and y direction and rotate it depending on the value. So if you remember, I was generating between -0.5 and +0.5. So roughly 50%, not quite. If it's greater than 0, I'm going to set the rotation to 0 degrees, otherwise 90 degrees. So then I've got an array of lines in a grid with random rotations, and this is where I'm making my grid, and this is where I'm just repeating the lines because I can. And in the future generations, you will see that you might want to change this a little bit so it's not always the same starting value. And then my random numbers at the end. So that just gets passed into this giant ugly lambda, and I pattern match everything out of it so I can plug it into the program again, right? So this is kind of how a basic structure you can get started in just getting a random value or list of random values and then put it into a program. Right, so let's talk about the exciting algorithm stuff. So what do I mean by shepherding random numbers, or at least by the guy who coined it, what does he mean by shepherding random numbers? It's really a way to create the illusion of order out of pure random stuff. So if you want to work with pure randomness, as in you don't have a basis of data to work from, you're not working with real-world data, there's no universality, there's no sort of pattern, how do you make things that look like it's got pattern? Well, you can do this. So you generate a list of random numbers, as you do. So in this case, I've just got a list of example 5 random numbers. And then I'm going to accumulate them. So I add it from the left to the right. So for each one, I add the next element, put it there. And then add the next element, put it there. So I create a new list of the running sum. Right. So now I got a list A, which is random numbers. A list B, which is a running sum of the random numbers in A. And I just shepherd them, as in I walk through both A and B, and then I apply it to some starting state. So my starting state might be just natural numbers or whatever it is, 0 to 4. And I'm just going to add both lists together, which this gives me the benefit of I have a whatever the starting state might be. So if my starting state is a line, a grid, a circle, there is some kind of shape. But then because I'm adding random values and applying both of them to it, there's enough chaos in the random number that it looks random. But because it's keeping a running sum, chances are it's going to be adjacent to the previous random value. So it kind of feels like it keeps some kind of shape, even though it's pure random. And this is what it's going to look like. So I've got a list of lines, and the lines have more segments than just the beginning and end points, so I can move it around, right? So I just started with a horizontal line. I move it downward, as you can see. So I'm going to apply some randomness to it. I'm just going to create, shall we say, the 2D list, a list of lists of random numbers. And depending on my random number between -5 or 0.5 and +0.5, I'm just going to move the points a little bit on the list. And then this is where magic happens. You add the random numbers and the running sum, and I'm going to fix it to the y direction, and guess what? You get this. So once you apply the two running sums, because they're kind of next to each other, and I'm adding each previous random values to not only on the line itself, but also to the previous line, I get a nice draping effect. And this is something you can just kind of get it running whatever you want. You can apply it to a grid or something like that, which you can see later. So just like this previous similar model that we plunged, in this case, I've decided that my model is going to be that, and the random value is going to be two properties. It's going to go like a list of floats and list of floats to kind of say this is my x and y's, but in 2D. And here I've got a really messy sort of list of maps and maps because I just work in list maps. I just love it so much. I'm just applying the adding function. The map to first is just basically list dot map to and tuple dot first composed together. And I'm just saying for each random value in A, for each random value in B, and all the accumulated stuff, just add it all together. I don't care. Just add it. And then after I added all of these from the lines, I just draw them again through a list dot map. And that gives you this previous really nice effect. And you can try this over and over again. You'll get different results. So it's pretty cool. So running a little bit quickly, I'm going to jump straight into a couple of examples. So if you were to increase the random values a bit more on the y than on the x, so for example, if you set the random value of the range between -0.5 and +0.5, but on the y, you kind of say, I want a -2 to +2. You'll get something like this, right, where your y values are a lot more exaggerated, and you can plot a circle somewhere in the side to say that's the sun, that's the moon, depending on how you see it. Or you can start with a circle, right? You draw a circle of lines, and you just draw lines like that. So they look like those radial sun shape. And in this case, I just didn't care about which way it goes. I just apply a high randomness in the x and y value, and again, add it together from this way and all the way that way. So it feels like the ring is kind of going through some seemingly logical pattern, but it's not. It's just random. But you can still follow the rotation here and there as well, depending on which way you go. OK, so number 3, L systems. I was speaking with a bunch of people last night, and it seems like everyone has done L systems in universities, or maybe not everyone, or maybe you forgot. Well, here's a bit of a refresher. L systems is a rewriting rule set. I won't go into the whole theory of how everything behind it, how it came about, but I'll just tell you sort of how the simplest L system works. It was originally created to simulate plants to kind of figure out, given a previous state, where would the next leaf or where would the next branch, and it's used a lot in the movie industry and I guess by biological computation people to kind of draw and make these created sort of artificial plants. That looks really cool. And you can kind of think of it like this. So this is one of the simplest L system you can imagine. I have 4 different things that can possibly happen in my state. And I'm going to call them DSLR because I really love cameras, and I really see one right there. But you can also imagine that in the textbooks. It's called uppercase F, lowercase f, plus or minus, same thing. When I see a D, I'm going to draw forward whichever my forward is going to be, right? When I see an S, I'm going to jump. So I'm not drawing. I'm just going to go to the next spot in the same unit distance. If I see an L, I'm going to turn left. If I see an R, I'm going to turn right. And I can set the angle of the turning to be as big or as small as I want. And depending on how much you set it and how the states come about, you will get very, very different results of drawings. That just depends on your rule set. So this example is I'm going to start at 0, 0, which is just somewhere like right there. And I'm going to say angle is 0 degrees, which in math is to the right, I guess. And the starting state, I'm going to say it's dr, 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 d, something like that. So I'm just going to draw one there, turn right, draw one there, turn right, turn right, turn right. That gives you, a rectangle. And the interesting thing about L systems is that once you apply a rule set to this starting state of 7 things, you get very interesting results. Like, I'm going to apply this super random and complicated thing, right? I'm going to say for every D that I have in my starting state, I'm going to replace it with DD, RD, LD, RD, RDD, which just gives me the little long rectangle and then back to the next starting state. That's all it's doing. So I'm going to start there. For every D in the starting state, I'm going to replace it with the green stuff, which is a new one. And you can see that the second iteration becomes that. And you can do this again and again and again and again. And it just goes on forever. People have used L systems to modeling fractals, to model plants, to model bricks, all kinds of repeating patterns. And the cool thing is that it's not just like a repeating pattern. You can do something very, very different, tweak a little thing, everything just change a lot. So it's nice for experimenting, and once you have your rule set down, it's very fun to play with. It doesn't really require too much thought after just changing a little bit here and there. So why not implement it in OWM? So this is the simplest L system I can come up with, at least in a way that it's easy to use. It's probably not the most strict way to implement it, but for me, I love lists. If you haven't noticed, I'm just going to do it this way. So I'm going to say for every rule in my L system, it's going to take whatever, I don't care what it is, and I'm going to say this rule turns whatever this thing to a list of whatever this thing is, right? So my rule can generate a bunch of stuff given the starting state. And then I'm going to say I can apply, so iterate the L system state from one to the next by saying I'm going to apply a rule to a list of states. Could be the starting state, could be the next state, and then give me the next state, right? So here I'm just saying, OK, I'm going to map every rule to this state, and I'm going to add them together again. So I inspect every element on the list. If I see one that matches the rule, I'm going to apply it, and I'm going to concat it back again. So I get another just one-dimension list, and I can just keep doing this. And this gets longer and longer and longer. So for example, if you were to implement the turtle graphics, this is what you get. My states are DSLR, as you've seen before. And the turtle, which is kind of a way for me to translate each state into SVG. Because I still have to say, even though I can apply these DSLR things, I still have to translate that into some kind of drawing thing, right? So I just say, I'm going to pattern match when I see the final state. So just to have some clarity, I call a turtle function when I have a bunch of these, right? So it's already been generated. And for each D, I'm going to move it. For each S, I'm going to just kind of jump to it. And then if it's L or if it's R, I'm just going to change and modify the angle. And here, I'm kind of exploiting the map accumul function, which just keeps a running accumulate calls of functions in Elm. And it just creates this giant list of all the previous iterations that's been seen before. In this case, I'm accumulating the angles and the different states. And then once I'm done with it, I grab the results, which has the starting thing and the running sum of whatever that's going to be. And I'm just going to take this thing out, and I'm going to concat all of this so it flattens it into like one level list again, which then I can use to plot. So I think I've exploited list quite a bit so far, but hopefully it's going to be OK. So that's also wrapped up in a package. You can, if you use Elm, feel free to check it out. So there's the explanation of what the state might look like. So you can imagine that I've defined my rules like that. So I say D is blah, whatever that is. And then the rest might change, might not change. And once I've defined my rule, I can apply these rules to whatever state. So you can also do really interesting things like generating what's called a space filling curve or the Hilbert curve. And there's also like, fractals, all kinds of stuff. You just have to look up I think everything you can imagine about L systems, it's been around for like, 50 years. You can find it, some kind of recipe, and it's just a lot of fun to play with. OK, so I've kind of rushed quite a bit of things, but I still want to tell you a little bit about the pen plotter. So before I go there, let me just kind of get started on this. So let's think about, I really tried a Hilbert curve before, but I really like the curtain. So I don't know, unless you have any preferences, I'm just going to go with that. So I've set it up before, I've tested it, and I hope it's still going to work. So let's just see. Oh yeah, it's moving. So I've got a bunch of small commands that sends over HTTP, and that's kind of local server running on my computer, which then talks serial. Anyway, so I'm just going to start it. I think if I erase it first, it would be safer. See how it goes, right? Everything is stateful over there, so you never know. All right, so if we can have the slides back for a little bit, that would be great. So let me just change this back. So because Elm doesn't really give you conversion to HTML row string, so for example, you can generate all the SVGs you want. You can't really convert the SVGs into a string that just says less than SVG, blah, blah, blah. So you can't really get that without running the Elm program still. Or at least you can try it, but there's no sort of officially, this is the way we're going to do it forward way. So there's not really a stable library that does it. And because Elm shields you away from a lot of the stateful stuff, which includes the DOM states, even if I've created everything and I generated my pattern on my website, shall we say, I can't actually get the inner HTML property in my DOM element, so I can't just grab the resulting SVG out. So for the moment, I'm going to use port, which is Elm's way of kind of interfacing with JavaScript. So you do it like this. You define a port, and the port, I'm just going to call it prints. So I just kind of hit print, and it's drawing nicely. Awesome. And port takes one built-in Elm thing. So it could be a string, could be a number, could be a Boolean, could be a tuple if you wanted. And it always returns a command. So this is, if you remember, this is Elm's way of saying, I'm going to do something on the side now, don't worry about it. Then when I come back, I'm going to wrap it in the message of your own definition. So in this case, I'm going to define my port function in JavaScript. So, JavaScript. I'm going to say that's the print that's exposed by Elm, and the subscribe is the built-in Elm function in JavaScript that tells JavaScript what to do when someone calls this thing in Elm, right? So here I'm just saying, yeah, I want to get my document, please, because I can't get it yet. And I'm going to grab the node, so the text in HTML, pass it, wrap it in the JSON object, and then just send it via HTTP post. So it's the simplest thing you can imagine. And you can do the post in Elm, but I didn't want to do 2 round trips. If I'm already in JavaScript land, I can just do it there. So it's easier. And yeah, this is another thing I've kind of did probably 2 nights ago now, but since that's running, I don't need to switch, so that's fine. You can see it, there's resources. Do you want to switch the screen thing back down to the pen plotter for a moment? You can see that it's running now. Probably a bit difficult to see the details because it's still at the very top. If you remember, when it draws to the bottom, it's going to start to drape, right? So since I got some time, maybe 5 minutes, do you want to take questions while I'm kind of like waiting for the pen plotter to finish? Great. Yeah, can we go back to the slides for a bit? Sorry. Let's go back. So I'm going to guess, and this is me not sure about what the community is like, because every talk so far has been a different language. So it's interesting. The first thing you might not, sorry, are you coming from Haskell, Clojure?
Yeah, Haskell.
Haskell, okay. So the first thing that you might not know is what these are. If you were here this morning for Joe's talk, these are the pipe operators, the exact same thing. This is $sign in Haskell. So it's just saying, compute everything on the right, and whatever you're done, pass the result to me in my function. And then another thing that you might not know from Haskell land, let's see. That's just pseudocode, so that's not really anything like that. Anything else? Anything else? So that's the same pipe operator again. Pattern matching is the same syntax. Double plus for string concatenation here. I'm using the pipe operator again. And you can pattern match like that in Haskell as well. Is there anything else that I missed?
Yeah, sorry. The question was, your random number generation functions are pure? Are they? And if yes, how do you thread the random number generator through, for example, through the list to generate a list of random numbers, those kind of things? Do you use state models or something?
So the random generator, so I won't answer the question about whether it's pure or not because I don't have the expertise to tell you about it. But what I can tell you is that the random package, along with random.extra in a community package, provides all kinds of ways to create all kinds of shapes in data structure that your random thing might be encapsulated in, right? So if you think about you want to generate a random thing from a list of things, or you want to take a random number, or you want to compose it in a record or something like that, there's all kinds of functions that will let you compose something that is a generator of whatever this is. And at the end of the day, you just take random.generates, and then you pass a message in Elm, and then you're followed by a generator of whatever that is. Elm then will do that in an update cycle, which to my understanding is happening, that's probably not pure, but the way that it wraps up in this logic, as far as your code is concerned, it is pure. But when it comes back, you will get a draw, go back. You will get a draw message, and here you've now got back to whatever data model you've decided to use. So in a sense, you can consider it's, I don't know, pure or not pure, but you can get that back once you've encapsulated your random structures. So in this case, it's just a list of floats, but that could be anything. If that answers your question a little bit. Okay.
Any other questions?
So what information?
Thanks. Once the information leaves your Elm program via JavaScript port via that post, where does it then go after that? Is it simply HTTP on the plotter, or have you got some middleware in the pipeline there?
So one thing I didn't introduce, because this is not an Elm talk, is that I've only done one half of the port, right? So I've got subscribe. There's also .send in the JavaScript exposing part of Elm inside the ports. So you can also send stuff back from JavaScript to Elm, and that's going to be a JavaScript value, which then you have to decode in Elm or encode in some way before you can talk to each other. But once you've done that in encoder decoder, it's quite easy to just transition between the two. Or you can choose to not send. In my case, I've just kind of sent it to http.post in JavaScript. So because when I do a command in Elm, it never really returns until there's a .send. So Elm has another way called subscriptions that listens for anything that gets sent back in a particular port, if that makes sense.
Yeah. So where does the information go once it leaves your program to get to the plotter, was the question I had.
Okay, so here I've just said to print, right? So if you could go back to the slide for a little bit, if you don't mind, so I can show you my answer alongside with the code. So here, I've said that my print takes a string. That string is actually not being used, right? So in my JavaScript function, I've effectively ignored whatever I'm going to passing, but I have to pass something, and Elm doesn't have the understanding of null or empty, or it does with maybe nothing. But other than that, I'm not actually using it because I can't get the DOM content inside Elm, which is considered stateful by Elm. I have to do that in JavaScript. So in this case, I could have pass the other HTML back into Elm with a .send between these lines, pass it to make sure it's validated and it's in whatever shape that I want. Then I do it in Elm. I have another way to pass the post network as well. But I figured since I'm just kind of playing with this, I didn't really need to validate it. I've already generated out of Elm. I can just straight away send a post. So you can see that I've gotten the document value straight from the browser. And here, I'm not touching the Elm program after that. But Elm does have a render function in Vue that populates it first.
Okay, thank you.
Yeah. So you can see that I've got a little playing website here, and each time I press it, it's going to be different, so I can play with it. And this is just, in a browser, right? So once I've got it, I can do whatever I want in there. So.
Cool. We're out of time for questions, but Xavier is going to be around, and you can probably catch him in the break. And we're going to break for lunch now, so join me in thanking Xavier for the talk.